Hi guys, so this is the first formal reach ahead lesson that we're doing, and this one's on a topic called formal charge. I just want to make a quick note to say not every reach ahead lesson will have a video component where I actually teach it to you. Sometimes I'll expect you to teach yourself based on a worksheet that I give you, but for this one I am going to do some instruction. So follow along. Remember, one thing I've noted on these is I'd like you to either make a folder in your OneDrive where you keep all of your reach ahead lessons, or if you really want to do them on paper, totally understand that because it's a lot easier to draw, and you don't want to scan and send them to yourself or anything like that. But I'd ask that you get a separate binder or separate duotang to keep track of all the reach ahead lessons. But just for my sake, I'd like them all to be in one place so I don't have a devil of a time when I go to mark them, and I want to, be able to treat it as one complete portfolio. So I'm excited that you guys are doing this. I hope there's lots of people joining in because I think it's a cool chance for you guys to get a few more marks, but much more importantly than that, a cool chance for you to really dig into some of the content that's a bit more interesting in the course that we just wouldn't have a chance to get to otherwise. So with no further ado, formal charge. Okay, so you've learned this unit about how atoms form hybrid orbitals to make molecular compounds. But if you've been paying attention, we've also been breaking rules when we made our Lewis structure. Maybe you noticed or maybe you didn't. But I want to give an example, which is that we're going to make the nitrate ion. So hopefully you remember that nitrate has a formula of NO3 and a charge of -1. And so if we go to make a Lewis structure, we know that nitrogen is going to give us 5 electrons in its valence, and that 3 times oxygen gives us 18. Excuse me. And the charge is going to give us 1 more, and that gives us a total of 24 electrons. And so when we go to do the Lewis structure, the least electronegative atom here is the nitrogen. So it goes in the middle, and we surround it with 3 oxygens. Just like that. And then we fill in the octet of each of these surrounding oxygens. All right, and then we count electrons, and we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 electrons. And the clever amongst you will note that that's exactly how many we're supposed to have. So we have to remember, of course, that we need to make a double bond here. So I'm going to make it right here on the top. And at this point in the course, we say it doesn't matter where we make it. Next lesson, we'll see that it does. But for now, it doesn't matter where we make it. So we make it there, and we're done. But if you look closely, you're going to see a problem. And the problem is that for this structure to work, nitrogen is making 4 bonds. But nitrogen's not allowed to make 4 bonds. Nitrogen, if you remember, is supposed to make 3 bonds. What to do? And then if you look, 2 of the 3 oxygens are only making 1 bond. But of course, oxygen should be 2. So we have atoms here that are breaking the rules, all right? And if we look closely, we can draw electron configurations for these. All right, so if we look at nitrogen, nitrogen here is sp2 hybridization, right? Because it's making 1 pi bond. So it's an sp2 hybrid, and it has 0 lone pairs. It has 3 sigma bonds, and it has 1 pi bond. And so if we draw that, we would say, okay, well, nitrogen's valence then, actually we can draw even the full electron configuration. That's all right. So we could say its 1s is full, and then we look here and it says that its second shell should be sp2 hybridized. So we have a 2sp2. That's going to give us 3 orbitals. And we also have a 2p, and there's 1 orbital there, right? Because sp2 hybridization leaves us with 1 p orbital to make a pi bond. And if you look here, it says that all of these are going to make bonds, 3 sigma bonds and 1 pi bond, which means that each of these orbitals can only have 1 electron. And there we go. Now, if you note, this only has 4 valence electrons, despite the fact that we know that nitrogen should have 5 valence electrons, right? When we did our count here, we said that nitrogen typically has 5 valence electrons. But here, when we do our electron configuration, we see that it only actually has 4. Likewise, if we look at these single bonded oxygens, we have 2 of them. Those are sp3 hybrids because they're not making any pi bonds. So they're sp3 hybrids, and they each have 3 lone pairs of electrons. They're making 1 sigma bond, and they have no pi bonds. And so again, if we quickly want to make electron configuration for this, we would say that the 1s orbital has 2 electrons, and then the 2 sp3 hybrid should be 4 shells, and 3 of those will have lone pairs of electrons, and the 4th one will only have 1 electron so that it can make a single bond, a sigma bond. And if we note, this is 7 valence electrons, not 6. Right? And again, that's problematic because oxygen, we know, normally has 6 valence electrons, right? So we said 3 of them gave us 18. And then we'll take a look, and the last oxygen is behaving normally. It's making a double bond, which will make it sp2 hybridization, and it's got 2 lone pairs, 1 sigma bond and 1 pi bond. And so we show that by saying it has a 1s orbital that's full. It has 2 sp2 orbitals, 3 of them, and a 2p orbital, just 1 of them, the leftover one. The p orbital has a single electron to make the pi bond. One of these has a single electron to make the sigma bond, and the other 2 have lone pairs. And if we just note really quickly, 6 valence electrons, which is exactly what we expect. So one of the oxygens is behaving the way we would expect it to, but everything else is weird. This has 1 too few electrons, and these both have 1 too many electrons in their valence shell. And so this seems to break the rules, but it actually introduces our new topic, which is the idea of formal charge. All right? So nitrogen has fewer valence electrons than it typically would. Oxygen, in this case 2 of the 3, have more electrons than they typically would. All right? And one of these extra electrons exists because the thing has a charge. If you look, this is NO3 minus 1, so it's gained 1 electron. And that would explain why one of the 2 oxygens has 1 too many electrons. But the other case is simply that obviously oxygen has taken 1 electron from nitrogen. A transfer has happened. And during molecular bonding, that can happen. We can have electrons moving from one atom to another. When this happens, even though the molecule on the whole may be neutral, individual atoms can take on charges, and we call these formal charges. And to calculate the formal charge, we use this formula. And it's right here on the next page. The formal charge is the atom's valence minus the number of bonds it's making. All right? Note not the bonding electrons, but just the number of bonds, and then minus how many electrons it has solo. And note this is not pairs. It's individual electrons that you have to subtract. So it gives a few examples here. it gives an example of carbon here, in this case, making 4 bonds, 2 single and 1 double. And so carbon's valence is 4. In this case, it's making 4 bonds, so we subtract that. It has no lone electrons, so we don't have to subtract anything there. And 4 minus 4 is 0. So in this case, carbon has a formal charge of 0, which means it's making the expected number of bonds. Or more to the point, it has the expected number of valence electrons. Right? And either way works to think of it that way. Now here, carbon's only making 3 bonds, so we already know that something's not right about that. But if we look, we'll see that that's 4 electrons that it should have in its valence, minus only 3 bonds, and that gives us a formal charge of +1. In other words, carbon doesn't have as many electrons in its valence as you would expect it to. And I'm not going to go through all of these examples, but I hope you see that we can count on any of these. I'll do one more maybe. In this case, nitrogen is making 2 bonds. So nitrogen has a valence of 5, and we subtract the 2 bonds that it's making. There's one, there's the other. And that isn't done the whole story though, because this also has 4 lone electrons. Remember, it's not pairs we're counting, it's the individual electrons. So we also have to subtract those. And 5 minus 2 minus 4 gives us a total of -1. And that means that nitrogen here has 1 more valence electron than it typically would, right? Because it has to have 1 electron in each of these hybrid orbitals to make those bonds. So that's 1, 2, 3, 4, 5, 6 electrons for nitrogen in its valence, when normally it would only have 5. So we say it has a formal charge of -1. So it's kind of nicer in a way to look at that if we take an example. So let's come back to nitrate right here, and let's calculate the formal charge of each atom on the nitrate ion. So first is the nitrogen itself. And remember, what we're doing is we're taking the valence, subtracting the number of bonds, and subtracting the non-bonding electrons. So for nitrogen, we look and we say nitrogen has a valence typically of 5, but here we have to subtract 1 for each bond. So 1, 2, 3, 4. We subtract 4 for the bonds, and then we have to subtract the number of lone electrons it has. And if we look, it has no lone electrons, so we're subtracting 0. And so nitrogen has a formal charge of +1. We could show that right in there, just like that, except way better than that. Just like that, we would show that it has a charge of +1. And then we could look and we could say, oh, there's 2 single bonded electrons, or single bonded oxygens, and they're the same, so we can treat them as 1 in terms of doing the calculation, because they both have a single bond and 3 lone pairs. Single bond and 3 lone pairs. So since they're identical, we just calculate once. And again, we say that the formal charge is the valence, in this case 6, minus the number of bonds. They're both just making 1 bond, and then minus the lone electrons. And there's 1, 2, 3, 4, 5, 6. And 6 minus 1 minus 6 means that these have a formal charge of -1. So -1 and -1. And then lastly, there's the double bonded oxygen. And the double bonded oxygen, again, has a valence of 6, but this time we're subtracting 2 for the number of bonds, because there's 1 bond, and there's another, so we subtract 2. And then we subtract the lone electrons, and there are 4 of them. And when we do that calculation, 6 minus 2 minus 4 gives us a formal charge of 0. And we don't have to draw that on the molecule. And so there we go. And again, we would show this right on the molecule by writing the plus or minus inside the structure like that. And I just want to make a note that if we take the sum of the formal charges, well, nitrogen, the formal charge total is going to be the formal charge of nitrogen plus the formal charge of the 3 oxygens. And in this case, that means it's going to be 1 minus 1 for that oxygen, minus 1 for the second, because remember there's 2 of them, and minus 0 for the final oxygen. And when we do that, we get a total formal charge of -1. I just want to note that the sum of the formal charges matches the charge of the ion. And it has to, right? We say that this oxygen has a charge of -1. That's canceled by the +1 of nitrogen. But this oxygen also has a -1. And so overall, the entire thing is -1. So anytime you take the sum of the formal charges, it should equal the overall charge of the ion. Now, why do we even bother with this? Why would we do it? Well, knowing the formal charge is meaningful because they give us an indication of whether or not a structure is likely to actually occur. In nature, structures with no formal charges are always possible. So any structure that has no formal charge can always happen. Whereas structures with a formal charge of +1 or -1, they can also occur, though they're less favorable. So if there's a choice between no formal charge or a formal charge of 1 or -1, the no formal charge one will happen. But sometimes we have to take a formal charge, like the nitrate ion. If you look here, there's no way to put this thing together that satisfies everything's octet rule and leaves you with no formal charge. So you have to use one. But what can't happen is formal charges more dramatic than that. So you can't have any formal charge of ± 2 or more. That's just too unstable, too much instability. And just remember that the structure with the lowest formal charge always wins. It's always the real one. So for example, carbon dioxide. What's the structure of CO2? Well, I'm going to suggest that there's 2 ways we could draw it. We've never thought about it before. We obviously know the one we intuitively do, which is we put carbon in the center, we put oxygen around it, we put sigma bonds between them, and before we did that, we'd count, of course. We'd say carbon should give us 4 electrons, 2 oxygen should give us 12, for a total of 16 electrons. So we'd come down here, we'd complete the octet of both of the oxygens, and then we'd count how many electrons we'd have. And of course, this one has to start the exact same way, because you can't break the rules of the octet. We always have to have valid Lewis structures before we can look at formal charge. But over here, I'm going to do the one we just commonly think of, which is I'm going to take one pair there and make a bond, and take another pair there and make a bond. And now we have a stable structure, 16 electrons total, but carbon is making 4 bonds, oxygen is making 2 bonds. Everything has a full octet, it's stable. I'm going to say there's another way we could draw it. I could take this oxygen and make 2 pi bonds. All right, we call that a triple bond. So here I've used 2 double bonds. Here I've used a triple bond. Well, both of those structures work. If you look over here, oxygen has a full octet, 2, 4, 6, 8. Oxygen has a full octet, 2, 4, 6, 8. And carbon has a full octet, 2, 4, 6, 8. So both of these structures work. Do they both happen in nature? Well, the answer comes from the formal charge. So here, if we treat this as oxygen 1, let's calculate its formal charge. Well, it's the valence, which is 6, minus the number of bonds, which is 3, minus the number of unshared electrons, which is 2. And that gives us a formal charge of, excuse me, +1. In other words, what it tells us is that that oxygen has 1 fewer electron in its valence than you'd expect. It's only going to have 5 electrons in its valence. But if we look at oxygen 2, it has a formal charge of 6, and then -1 for the 1 bond it's making, minus 1, 2, 3, 4, 5, 6, 6 lone electrons, and that gives us a formal charge of -1. And then lastly, we have carbon. Carbon has 4 valence electrons. We subtract the 4 bonds it's making, and then we subtract the 0 lone electrons it has, and it gives us a 0. Now note that this is still a possible structure. We said that any structure that has no formal charge is more dramatic than +1 or -1 can happen. Furthermore, if we take the sum of these sum out to 0, right? As they should, because carbon dioxide is neutral overall. But if we find the formal charges over here, we find that oxygen 1 now has 6 valence electrons, -2 for the 2 bonds it's making, and -4 lone electrons, and that gives us a formal charge of 0. And then the second oxygen has the exact same composition, so 6 minus 2 minus 4 is 0. And then this carbon has a valence of 4. It's making 4 bonds and has no electrons, so it's 0. So both of these structures work. Both of them give us net charges of nothing, but the structure on the left requires one of the oxygens to have a +1 formal charge and another to have a -1 formal charge, whereas the structure on the right doesn't require any formal charges. And that makes this structure the one that actually happens in nature in appreciable quantities. So this is the real structure of CO2, the real observed structure, and this is not seen in nature. Because the energetically favorable conformation is the one that doesn't require us to have a formal charge. The last thing I'd say is, can we eyeball this? Yeah, you can, right? We don't always need to calculate the formal charge of an atom in a compound because we can see really quickly by looking at how many bonds each atom makes and comparing it to its known carrying capacity. We know that carbon normally makes 4 bonds. So if carbon is making 4 bonds and has no lone pairs of electrons, it doesn't have a formal charge. Nitrogen and phosphorus normally make 3 bonds. Oxygen and sulfur normally make 2. And if any of these are different, then we know it's going to have a formal charge. And then you can calculate it at first. Though eventually you'll even get in the habit of eyeballing them and just being able to look and see what the formal charge is. If an atom doesn't make a different number of bonds, or if it doesn't have the wrong number of valence electrons, it won't have a formal charge. So for the homework, I'd encourage you to try and see if you can do it by sight, and then go back and calculate each one and see if you're able to do it right. Really quickly, I'd just say, looking at this, you can tell that nothing here is going to have a formal charge because both oxygens are making 2 bonds, which is its regular carrying capacity, and carbon is making 4 bonds, which is its regular carrying capacity. Whereas on this side, you can see that the carbon won't have a formal charge because it's making 4 bonds, but that this oxygen is making 1 bond too many, and that's going to end up giving it a formal charge of +1, and that this oxygen is making 1 bond too few, and that's going to end up giving it a formal charge of -1. Right? We can eyeball it. We don't actually have to sit down and calculate it every time. Likewise, if we come here, back to this structure, we can see that nitrogen was making 1 bond too many. We expect nitrogen to make 3 bonds according to its carrying capacity, and yet this one makes 1, 2, 3, 4. So that's going to give it a +1 charge, 1 too many bonds. This oxygen is doing exactly what it should. It's making 2 bonds as expected. But this oxygen's only making 1 bond when it should be making 2. That's 1 bond too few. So it'll have a -1 formal charge, and it does when we calculate it. Likewise, this oxygen's making 1 bond too few, so it has a -1 formal charge. And that's how you can eyeball these things. So good luck, enjoy the homework. This is the first of a handful of reach ahead question assignments you're going to get. It's the first of 3 for this unit. Thanks a lot. Bye.